CHEM 2212 ring opening of 1,2-epoxy hexane under acidic conditions and under basic conditions. We're going to divide this up into two parts. The first part will be the acidic reaction. So we're going to do this under acidic conditions with concentrated sulfuric acid. So the first step is for us to take our 1,2-epoxy hexane and measure out 0.5 gram in our 14 by 10 round bottom flask. Go ahead and tare our balance here. And we'll just measure this out drop by drop. Okay, we'll put the top back on just to make sure we've got an accurate number. And I'm going to write this down on my data sheet. So 0.516 grams of our 1,2-epoxy hexane. We'll transfer this over to the hot plate, the stirring plate, to finish the setup. All right, we'll gently lift this up. I want to make sure that the flask doesn't fall over, and I'll transfer it over here to our stirring plate. And we're going to dissolve our epoxide with 5 mils of methanol. Okay, there's our methanol. I'm going to go ahead and put in our spin vane so that we can get this stirring. Turn this on gently. We don't want it spinning too fast. Don't want to accidentally knock over the flask. And that looks pretty good. So the last part of our setup here will be the addition of our concentrated sulfuric acid. We're going to use a single drop to start our reaction, then we're going to allow it to stir for 30 minutes. I'm going to do this well under the snorkel because it is very dangerous to breathe in concentrated sulfuric acid fumes. All right, there is our drop of sulfuric acid. We're going to let this stir for 30 minutes and come back and check on it. So our reaction is stirring for approximately 30 minutes. We went ahead and added to our data sheet the starting volume of our methanol, which is 5 milliliters, and the approximate volume of our sulfuric acid, which was a single drop of our concentrated sulfuric acid. We'll add our stirring time after we get finished in about 30 minutes. So our acidic solution has finished stirring. We've been stirring for roughly 35 minutes. We're going to go ahead and take this off. I'll turn off my stir plate. And we're going to transfer this into a 125 ml separatory funnel, making sure that our stopcock is closed. Pouring it through the short stem funnel so that I can catch my spin vane. I'm going to go ahead and pour in 5 mils. We're going to wash our solution with 5 mils of sodium bicarbonate solution. This is a saturated solution. I'm going to pour it into my original reaction vessel and then pour it through the short stem funnel into the separatory funnel. Okay, and then into our separatory funnel through the top. And let's focus on the solution here. You can see a lot of bubbles forming in the funnel here. So we know that we had strong sulfuric acid as our catalyst. We've now poured in saturated sodium bicarbonate, so we can see a reaction going on in our separatory funnel. Also notice that there are no separate layers formed, so that was an aqueous solution going into an aqueous solution, right? Our methanol is miscible in our aqueous sodium bicarbonate. Okay. We'll go ahead and take our short stem funnel out. Put our stopper on, and I'm just going to swirl to make sure we get a good mix. Now we're ready to extract our product using diethyl ether. So we're going to go ahead and extract our product with 2 10 ml portions of diethyl ether. I've got the first 10 ml portion here. I place my short stem funnel back in the top of my separatory funnel, and I'll go ahead and pour this in. Doing all of this, of course, under our snorkel, because our diethyl ether is very volatile. So we take a look at our sep funnel, and of course now we can see 2 layers forming. Go back to your table of reagents, look at the varying densities of diethyl ether and methanol/water, because we know that we've got that saturated sodium bicarb solution in there as well for our aqueous solution, and figure out which layer represents the organic and which is our aqueous. Take out my funnel, put in my stopper, I'm going to go ahead and make sure that I'm holding that stopper in place, and I'm going to give it a shake. Make sure we get a good mix. I'll vent it up into the snorkel, close it again, and I'm going to do this 3 times. Okay, we'll go ahead and put it back in place, take our stopper out of the top, and we're going to let those layers separate for a moment before we drain off the bottom layer. So our layers have separated. If we take a look at our flask here, we've got a clear top layer and an opaque white bottom layer here. I'm going to put my Erlenmeyer flask underneath, and I'm going to drain off my bottom layer. Slow it down as I get to the interface to make sure that I don't accidentally drain off any of my top layer there. Okay, so there's my bottom layer. Now I'm going to drain off my top layer into a separate beaker. All right, top layer has been collected. Close my separatory funnel. Put my short stem funnel back in place, and I'm going to take my opaque layer and pour it back into the funnel. Okay. And now we'll proceed with the second extraction. I'm going to measure out an additional 10 mils of diethyl ether. There we go. Close up our ether. I'm going to pour this aliquot into the flask that held my bottom layer, my opaque bottom layer, just to make sure that I rinse out any possible product that might have been lost there. As we can see, there's still some particulate from our sodium bicarb solution. Swirl that around, and then I'll pour it back into the separatory funnel through the top. funnel aside, and I'm going to go through my extraction process again. Making sure that I hold that stopper on. Shake and vent. We'll do this 3 times just like before. Take our stopper off. I'm going to let the 2 layers separate and then drain off the bottom and the top layers separately once again. Looks like we've got full layer separation at this point. A little bit of bubbling at the interface. I'll give it a quick swirl. And we're ready to separate. I'll do just what I did before, which is drain off our bottom layer. A little bit remaining. Again, I'll give it a swirl. I want to make sure I get all of this bottom layer off. Okay, and the only thing that we have remaining is our clear, transparent top layer. Set that aside. I'm going to combine the 2 ether layers into the same Erlenmeyer. And these combined ether layers are where our product is located, or products. We'll have to think about what our product mixture may or may not be depending on the conditions, acidic or basic catalyzed reactions. So we're going to take this, dry it, because if you can see, we've got a little bit of water down in the base of our flask. In fact, what I may do instead, that's enough water that I'm going to go ahead and put it back into the separatory funnel, and we're going to drain off that little bit so that we don't have to dry all of that with mag sulfate. So let's do that. So if we take a look, we can clearly see, I hope that we can clearly see, that we've got a small layer of water here down in the bottom, our aqueous layer. So I'm going to go ahead and drain that off into our waste beaker, or waste flask. Okay. And then we'll drain our ether layers into a second flask. That's going to make the drying of this solution much easier. That's the nice thing about extractions. You can always pour things back into the separatory funnel and separate the layers again in case you have a little bit of overlap. All right, so that looks a little bit better. The next step will be drying this with magnesium sulfate. So let's do a data sheet recap real quick. So we've finished stirring our acid catalyzed epoxide ring opening solution. We used 5 mils of saturated sodium bicarbonate solution to neutralize our acidic conditions. We then extracted with 2 10 mil portions of diethyl ether, so a total of 20 mils. We're now going to dry our diethyl ether solution using mag sulfate, and we're going to decant it off into a pre-weighed round bottom flask. Now to dry this solution with mag sulfate, I'm just going to get a small amount tip of a spatula, and I'm going to add that in to our flask, and I'm going to swirl that around. And what we're looking for is to see if any of that powder sticks to the flask, right? If we see any clumping, what we know is that that mag sulfate has aggregated with water. And what I'm seeing is a lot of powder that is free floating, which tells us that we don't have much water, if any. It's clumped up just a bit. We'll put a small amount more in, just to make absolutely sure. Right, so another tip of the spatula. Another swirl, and all of our powder is free floating, so I think we look pretty good. The next step will be decanting this very carefully into a pre-weighed 100 ml round bottom flask. Upon careful reflection, once we looked at the total volume of solution that we're dealing with, which is about 20 mils or right at 20 mils, instead of pouring into a 100 ml round bottom flask, we're going to go into a 50 ml round bottom flask. So we're going to decant this very carefully. Decanting means that we're going to be pouring our liquid into our round bottom flask, but we're going to be leaving our solid behind in our 125 Erlenmeyer. Just have to be patient while doing this. You don't want to get ahead of yourself. We've still got a tiny bit of liquid, but I see a little bit of solid in it, so I'm going to stop pouring there. So we may still have some product in this Erlenmeyer. That's to be expected. That'll be one of our potential sources of error, but we wanted to make sure that we didn't pour any of this mag sulfate into our pre-weighed 50 ml round bottom flask. If we take a look at our data sheet, I've written down here acidic conditions, 50 ml round bottom flask, and then our weight. We're going to take this over to the rotoevaporator, drive off the diethyl ether, and obtain our product. So we're here at the rotovap. We're going to use it to drive off our diethyl ether so that we can obtain our product mixture here in our 50 ml round bottom flask. In your literature, in the experimental procedure, it tells you to do this at room temperature. We're going to heat it up to about 30 degrees Celsius just to make sure that we drive off every last little bit of our diethyl ether, so that when we go through our GC, we're going to get the best possible data for you to use when calculating your percent yields and your product mixtures. So we're going to go ahead and attach our round bottom flask to our trap, just as we've done in the past. I'm going to use a cat clip to secure it because we don't want it to fall off into our water bath. I'm going to go ahead and turn on my vacuum. Now that hissing sound that you hear is coming from this. I'm going to go ahead and close that, which means we're building vacuum in the system. We have our second rotovap capped and closed. Remember, these are in parallel, so they have the same vacuum. So we have to make sure. You can see bubbling occurring already in our flask, so I'm going to go ahead and get it spinning. We don't want it to pop into the trap if we can help it. I'll put it down into the water bath. I'm going to shift my water bath forward just a little bit so the trap doesn't hit the edge. And there we go. So we're going to let that spin and heat for a little while under vacuum. and drive off our diethyl ether. We'll come back once it's finished and we'll weigh our final products. One thing that I want to bring to your attention as this is evaporating is, if you can see right here, we have this haziness. This is actually water collecting on the exterior of our round bottom flask. If I put my finger down, right, I clear that water off. That water is condensation. As we're evaporating our diethyl ether, the flask gets very cold. This is cold to the touch, and it starts to condense water from the atmosphere on the outside of the flask. We're finished with the rotavap. We've gotten all of our diethyl ether off of or out of our flask at this point. You can't smell any more in the flask. A quick wafting test tells us that our diethyl ether is gone. So I've tared a 400 ml beaker here, and I'm going to go ahead and weigh our flask and our product together. This is 48.231. So this is our flask plus product is 48.2. Now it's changed to 230. Okay. So we'll go ahead and do our subtractions and find the weight of our recovered product before we put it through the GC to obtain our final data. For the second part of our experiment today, the ring opening of our 1,2 epoxy hexane, we're going to be using sodium methoxide as our base catalyst. I'm going to weigh out 0.4 grams into our 10 ml round bottom flask. I'm very careful doing this. So I've made a little funnel out of weighing paper. And I'll just be dropping in little spoonfuls at a time. I just want to make sure I don't go over. So 0.4 grams. About halfway there. Oh, may have gotten lucky there. Go ahead and close up our bottle. Set that aside, and I'll put the top on here. So we've got 0.414, it looks like, 0.413, 0.412. We'll let it settle out here. 0.411 is our final weight. We're going to go ahead and enter that data onto our data sheet. We're looking for our starting weight of sodium methoxide, and it was 0.411 grams. Now we're going to move our setup over to the stirring plate and add in our methanol and our epoxy hexane. So we've transferred our aluminum block and our round bottom flask with our sodium methoxide in it onto our stirring plate. I'm going to go ahead and add in 5 mils of methanol and create our base slurry. I'm going to add a spin vane to our flask, just as we did with the previous flask. And I'm going to start stirring at around 400 RPM or so. We're going to let that mix for a minute. We'll go back over to the balance and weigh out our 1,2 epoxy hexane. So we're back over at the balance. We're going to be measuring out our 1,2 epoxy hexane. Once again, we're going to get 0.5 grams, half a gram of our epoxide. Make sure this is tared out. I'm going to be measuring this out in a graduated cylinder. Then we'll use a long-tipped pipette to deliver this into our reaction vessel. Okay, almost there. We'll put the top back on to make sure we don't have any air currents affecting our weight. And we're at 0.509. 0.509, we'll go ahead and write that out on our data sheet. Okay, and then we'll transfer this graduated cylinder over to our reaction mixture. Now our methanol and sodium methoxide slurry is stirring. This powder will not dissolve completely, so we don't have to wait on that. But what we're going to do is we're going to take a long neck pipette, push that off to the side, and I'm going to introduce our epoxy hexane into our reaction vessel. Make sure I get every last little bit out of my graduated cylinder. There will be a little bit of loss just because we're transferring vessel to vessel, but it'll be minimal. That's something you'll want to mention in your lab report. So we've added our epoxy hexane into our sodium methoxide and methanol slurry. We're going to let this mix for 30 minutes under reflux. Let's go ahead and set up our reflux apparatus. We're going to add a clamp above our flask. This is going to hold our condenser in place. Here's our condenser, microscale condenser, 1410, that matches the size of our round bottom flask. We have a brown O-ring that's going to give us our seal and our screw cap that will make the connection with our round bottom flask. So I'll go ahead and put that in place and screw it down. I'm going to move it up just a little bit. There we go. Okay, we've got to keep that centered so that our stirring will be undisturbed for the duration of our reflux here. We have our water tubing. This will be our inlet. Space here. Our inlet will go to, I'll just put it onto this one, our faucet. And then our outlet come out at the top, and that will go into our drain. I'm going to keep it out of the drain for just a second. We want to go ahead and fill the condenser. And we'll check the outflow on our outlet here. And that's pretty good. We don't need it to be too fast. Otherwise, we could blow a hose and cover our bench top in water. So I think we're set. Our solvent system is methanol. So we know that if we were to set our hot plate at around 70 degrees, or just a little bit above, we should get a nice reflux. We'll let that heat up and we'll come back once the reflux is started. So we had to bump our temperature up just a bit to about 112. We were getting some heat loss between the hot plate and our aluminum block, but now we have reached a comfortable reflux. We're going to let that reflux for 30 minutes and then we'll come back for our extraction. Our base catalyzed reaction mixture here has been refluxing for roughly 30 to 31 minutes. So we're going to go ahead and remove heat and let it cool down. I'm going to do that by undoing my clamp and lifting it up. And then I'm going to move my hot plate out of the way. We'll let that cool down for a few minutes and then we'll start the washing and extraction process. So our base catalyzed reaction mixture has cooled. We're going to go ahead and unscrew it from the condenser and take it over to our extraction setup on the next bench. So we have our separatory funnel. I'm going to make sure that the stopcock is closed. We have our short stem funnel. I'm going to pour this in through the top. And I'm going to use that short stem funnel to capture our spin vane, just like we did with our previous example. Okay. And we're going to neutralize this reaction mixture with 5 mils of our saturated ammonium chloride solution. I'm going to pour that into our original reaction vessel here, just so that we can get any remaining product rinsed out. There we go. Swirl that around a little bit. We can see a little bit of particulate here inside, so we're going to try and rinse as much of that down as we possibly can. And I'll pour that in through the short stem funnel as well. All right, so we see a little bit of bubbling throughout the solution. We know that we were base catalyzed for this reaction mixture. So we've just placed a weak acid, our saturated ammonium chloride solution, in to neutralize that base. We're going to swirl this just a little bit. Set this funnel aside for the time being. Just going to swirl the contents. Once we know they're good and mixed, notice that there are not layers. We have not formed any layers as a result of this addition. These are both aqueous solutions that are miscible in one another. Now we're ready to move on to our extraction. Now we're ready to begin our extraction phase. We have 2 10 ml portions of diethyl ether. We're going to do those one at a time, just like we did with our previous extraction. In this case, we're going to be pouring our diethyl ether portions into our separatory funnel and extracting our product or product mixtures out of the aqueous layer and into the organic. So let's go ahead and pour the first portion in. I'm going to use my short stem funnel here. Okay, so first 10 ml portion. Set this aside. And if we take a look, we can clearly see the formation of 2 separate layers. One that is clear, transparent, the other that is opaque. Looks almost frosted. So we'll have to take a look once again at our density tables to determine which layer is which. I'll cap the top, carefully take it out of my ring clamp. I'm going to give it a shake. Vent it up towards my snorkel. Another vent, and we'll do it a third time with a third vent. We'll place this back in our ring. Take our stopper off, and let's check to see that our layers are separating. Now these layers have separated very clearly and very quickly, as opposed to our acid catalyzed extraction. So we see two very distinct layers. So we're going to go ahead and drain the lower layer into one Erlenmeyer. Being careful to slow down as we get close to the interface between the two layers. So that's our bottom layer separated. I'm going to collect the top layer in a second Erlenmeyer, just like we did before. All right, top layer has been collected. We'll set that aside. I'm going to place my short stem funnel back in, make sure my stopcock is closed, and then I'm going to pour the bottom layer back into the separatory funnel. Now it's time to extract with a second portion, 10 mil portion of our diethyl ether. Okay. Go ahead and put our stopper in and go through the same process again. Give it a good shake and vent. Shake and vent. Shake and vent. Remove our stopper and wait for the layers to separate. It's going a little bit more slowly this time, but we still see a clear separation. We'll give those layers a second to fully resolve, and then we'll separate them. So our layers have resolved. We've now got a clear bottom layer and a clear top layer. We're going to go ahead and drain off the bottom layer into our catch flask here. Being careful just to drain out the bottom layer, leaving the top layer in the sep funnel. Set that aside. I have my second flask that has one portion of our diethyl ether extract. We're going to combine it with the second 10 mils of diethyl ether. Now that we have all 20 mils of our diethyl ether extraction combined in the single flask, we're going to dry it with magnesium sulfate. So we have our magnesium sulfate here, anhydrous, the powder that we used previously to dry our other diethyl ether extraction. We're going to put in roughly the same amount that we did before, just the end of a spatula. That's a little bit more than the end of a spatula, but that'll be okay. We'll swirl it around, and we'll see, I think you can see that we have some of our powder that's stuck to the bottom of the flask, indicating that it's aggregated with water and started to clump. We have some powder that is clumped but flowing freely in solution. So we're going to put a little bit more in just to make sure any of our water or aqueous solution has been dried up. Give it a good swirl. And we've got a good amount of free-floating powder here, indicating that we've dried up all of the water that's present in this flask. Now we're going to decant this into a pre-weighed 50 ml round bottom flask so that we can drive our ether off using the rotovap. So we pre-weighed our 50 ml round bottom flask. I'm going to carefully decant our liquid from our flask, our Erlenmeyer flask, into our round bottom. Most important part of this process, of course, is getting all of our liquid transferred, but none of the solid. And that looks pretty good. Okay, so we have our product mixture, and our diethyl ether in this 50 ml round bottom flask. We're going to take it to the rotovap and evaporate off all of our diethyl ether. So we have our flask here with our diethyl ether and our product mixture. I'm going to go ahead and place that on the end of the trap on the rotovap, just like I did before. Secure it with a cap clip. We've got our water bath heating slightly. I'm going to turn on my vacuum line. Of course, you can hear that because the valve here is open. I'm going to go ahead and close that. And then we're going to quickly look at our flask. We should start to see some bubbling, just like that. We don't want it to bubble too violently. I'm going to go ahead and start rotating the flask and dropping it into our water bath. We're going to let this sit on the rotovap until all of the diethyl ether is removed. We've removed our product flask from the rotovaporator now that we've removed all of our diethyl ether. I've marked it with a B to go along with our A portion from our acidic. This is our acid catalyzed product mixture. This is our base catalyzed. I'm going to go ahead and weigh this out. Make sure it's tiered. We're at 42.795. 42.795 grams. Let's catch up on our data sheet real quick. We were finishing up for our base catalyzed epoxide ring opening. We did 5 mils for our saturated ammonium chloride. That was our initial wash. And then our extraction of 2 portions, 10 mils each, for a total of 20 mils of diethyl ether that we just removed from our rotovap. We just weighed our flask that was pre-weighed previously at 40.880 grams. And we've got 42.795 with our product in the flask. So we'll go ahead and subtract out. We got 42.795 minus 40.880. That is 1.915. 1.915 grams. That's the weight of our recovered product. And remember, this is a product mixture that we're going to be putting through our GC unit in just a second to see how much of one product over the other we obtained under given conditions, base or acid catalyzed. We're going to do the same thing up here for our acid catalyzed product mixture. So we have our flask weights down here. We've got flask plus product at 48.230 minus 45.470. That's going to be 2.76. 2.76 grams, so a slightly higher yield for our acid catalyzed epoxide ring opening. So we've isolated our acid catalyzed epoxide ring opening product mixture and our base catalyzed epoxide ring opening product mixture. We're going to inject each of these 2 liquid mixtures into our GC with the hopes that it can tell us which one of the two possible products is our major product, depending on whether we're acid catalyzed or base catalyzed. The data from these GC runs will be posted to ELC for you to use in your lab write-up.